Namaste and welcome back to JEE Chemistry with Typical Monk. This is class 13, Solutions. Dissolve a pinch of salt in water and something quiet but remarkable happens. The water now boils a little higher, freezes a little lower, and will push across a membrane if you let it. These are the colligative properties, and here is the astonishing part: they do not care what the solute is. They care only about how many particles it splits into. Today, we read Raoult's law, meet the 4 colligative properties, and weigh a whole molecule from nothing more than a drop in temperature. One idea at a time. Here is what you will learn today. First, the concentration terms, molarity, molality, and mole fraction. Second, Henry's law and Raoult's law. Third, ideal versus non-ideal solutions, the deviations and the azeotropes. Fourth, the 4 colligative properties, relative lowering of vapor pressure, boiling point elevation, freezing point depression, and osmotic pressure. And fifth, the Van Hoff factor, abnormal molar mass, and a set of drills. One idea at a time. 4 ideas. Run this entire chapter. Look at them together first. The concentration terms, molarity, moles per liter, molality, moles per kilogram, and mole fraction. And remember, molality is temperature independent because it uses mass, not volume. Henry's law. The solubility of a gas is proportional to its partial pressure, P equals Ka times X. More pressure, more gas dissolved. Raoult's law. Each component's vapor pressure equals its mole fraction times its pure vapor pressure, P equals X times P degree. And the colligative properties. These depend only on the number of particles in solution and never on their nature. That single fact is the soul of this chapter. Now, look at the picture. Vapor pressure plotted against mole fraction for an ideal solution. Raoult's law itself. Each component's partial pressure is its mole fraction times its pure vapor pressure, P equals X times P degree. The 2 partial lines. The pressure of A rises as its mole fraction, X arises. The pressure of B falls as X arises. Each one is a straight line. The total pressure is P up plus PB, and it too is a straight line, running from P degree B, when there is only B, up to P degree A, when there is only A. That straight total is the signature of an ideal solution. An ideal means the RP forces are equal to the RR and the BB forces, so there is no heat exchanged and no change in volume when the two are mixed. Now, the 4 colligative properties, 4 measurable shifts, all from a single cause. The solute lowering the solvent's tendency to escape. The relative lowering of vapor pressure, P degree minus P over P degree, which equals the mole fraction of the solute. The purest statement of the effect. The boiling point elevation, delta TB equals I times KB times M. The solution boils higher than the pure solvent. The freezing point depression, delta TF equals I times KF times M. The solution freezes lower. This is why we sought icy roads. And the osmotic pressure, pi equals I times CRT. It is the pressure needed to stop the solvent crossing a membrane, and it is the best method for very large molecules like proteins. Let us work the JEE favorite numerical, finding a molar mass from a freezing point. 1.8 grams of a solute in 100 grams of water lowers the freezing point by 0.186 degrees. The Kf of water is 1.86. Find the molar mass. The molality first. Delta Tf equals Kf times M. So M equals delta Tf over Kf over K, often 0.186, which is 0.1 mole per kilogram. The moles. Moles of solute equal the molality times the kilograms of water, 0.1 times 0.1, which is 0.01 mole. The molar mass. Molar mass equals the mass over the moles, 1.8 over 0.01, which is 180 grams per mole. This is glucose. Now, the Van Hoff factor. If the solute had dissociated into I particles, delta Tf would be I times Kf times, and a larger I means a lower apparent molar mass. So the answer 180, with I equal to 1 for a non-electrolyte. For sodium chloride, I is about 2, which doubles delta TF, and that is exactly where abnormal molar mass comes from. Now, what happens when a solution is not ideal? Look at the plot. The ideal straight line, and two curves that stray from it. The ideal dashed line, where the AB forces exactly equal the AA and BB forces, and the total pressure runs straight. A positive deviation. When the AB forces are weaker than the original ones, the molecules escape more easily. The vapor pressure runs higher than ideal, and the curve bows upward. Ethanol and water are the classic example, and it forms a minimum boiling azeotrope. A negative deviation. When the AB forces are stronger, the molecules are held tighter, the vapor pressure runs lower than ideal, and the curve bows downward. Nitric acid and water do this, and it forms a maximum boiling azeotrope. And the azeotropes themselves, mixtures that boil at a constant temperature, with vapor of the same composition as the liquid, so they cannot be separated by simple distillation. Now what JEE actually asks. 5 pointers. 1. Raoult's law. The partial pressure of A is x a times p degree A, and for an ideal solution, the total is x a p degree A plus x b p degree B. 2. The colligative properties depend only on the number of particles, never on their nature. 3. Delta TB equals IKBM, delta TF equals IKFME, and the osmotic pressure pi equals IKT, that I is the Van Hoff factor. 4. The Van Hoff factor greater than 1 for dissociation, less than 1 for association, and equal to 1 for a non-electrolyte. And 5. A positive deviation gives a minimum boiling azeotrope. A negative deviation gives a maximum boiling azeotrope. Now an assertion and reason drill. For each pair, are both true, and does the reason explain the assertion? First pair. Assertion. Colligative properties depend on the number of solute particles, not on their identity. Reason. They arise from the solute, lowering the solvent's escaping tendency. Both are true, and the reason directly explains the assertion. The answer is A. Second pair. Assertion. A solution showing positive deviation from Raoult's law forms a maximum boiling azeotrope. Reason. A positive deviation means the vapor pressure is higher than the ideal value. The reason is true, but the assertion is false. A positive deviation gives a minimum boiling azeotrope, not a maximum. So the answer is D. Third pair. Assertion. Osmotic pressure is preferred for finding the molar mass of macromolecules like proteins. Reason. Osmotic pressure is a colligative property. Both are true, but merely being a colligative property does not explain why osmotic pressure in particular is preferred. That is because it gives large, measurable values at low concentration. So the reason does not explain the assertion. The answer is B. Now match each property to its formula. Raoult's law goes to P equals x times p degree. The boiling point elevation goes to delta T, P equals IKBM. The osmotic pressure goes to pi equals ICRT. And the Van Hoff factor for dissociation goes to I greater than 1. 4 pairs, and each is worth committing to memory. Now, how many of these 3 statements are correct? 1. Colligative properties depend on the number of solute particles. That is correct. It is the definition. 2. A positive deviation from Raoult's law gives a maximum boiling azeotrope. That is wrong. A positive deviation gives a minimum boiling azeotrope. 3. The Van Hoff factor is greater than 1 for all solute that dissociates. That is correct. More particles means I above 1. So the answer, 2 are correct. Statements 1 and 3. The trap is statement 2. A positive deviation gives the minimum boiling azeotrope. Now the 2 mistakes that quietly cost marks. The myth. Colligative properties depend on the nature or the mass of the solute. The truth. They depend only on the number of particles. And that is exactly why the Van Hoff factor matters. It counts how the particles multiply or combine. The second myth. A solute that dissociates gives a higher apparent molar mass. The truth, dissociation raises I and the particle count, which gives a lower apparent molar mass. It is association, where particles combine, that raises the apparent molar mass. Now test yourself, answer before the reveal, and work the number in your head. That is how G speed is built. Here we go. Question 1. The Van 't Hoff factor for glucose. 1. It does not dissociate. Question 2. The Van 't Hoff factor for sodium chloride, fully dissociated. 2. Question 3. Delta TF. If Kf is 1.86, the molality is 0.1 and I is 1. 1.8, 6 times 0.1, 0.186 degrees. Question 4. The molarity of 0.5 mole in 2 liters. 0.25 molar. And question 5. A positive deviation gives which azeotrope? The minimum boiling one. Let us gather it all in one breath. Raoult's law, P equals X times P degree, and an ideal solution's total pressure is linear in the mole fraction. The colligative properties depend on the number of particles, relative lowering of vapor pressure, boiling point elevation, freezing point depression, and osmotic pressure. Delta TB equals IKBM, delta TF equals IKFM, and pi equals IKLT. The Van 't Hoff factor, greater than 1 for dissociation, giving a lower apparent molar mass, less than 1 for association, giving a higher one. And the deviations, positive gives a minimum boiling azeotrope, negative gives a maximum boiling one. Next class, electrochemistry, galvanic cells, electrode potentials, and the Nernst equation. A dissolved solute quietly bends the solvent's behavior. And because the colligative properties count particles, not kinds, a simple drop in temperature can weigh an entire molecule. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time. You will crack G. I will see you in the next class.